Caroline asked was why, when we were doing Riemann sums, we found that the exact, let's see if this shows up. Oh, can you do the, oh, you already are. We said that the exact area between y equals 4x plus 3 we said the exact area was 65 units. And the approximate when n is equal to 25, we got the area was approximately 67 units, square units. Did you get notes? And she wanted to know why. Why did we, for one thing, why did we bother approximating the area when we have a way to know the actual area? Well, because most functions aren't geometric. Most functions that we're going to look at, oh, you know what? Okay. Most functions are going to be more like, where did I just put it? Oh, here. So in this function, if our lines, let's say this is 7, and we're going between 2 and 7. If this is our region, we can't use geometry to find the area. So what we're doing is we're using the fact that we can use geometry on a linear function to test out some of the other techniques that we're learning. So I know how to find the area of a triangle and a rectangle. And if we do that, we know that the base is 5 here, base is 5. The height here is 3 because the y-intercept is 0, 3. And we said last time that since f of 5, and let's go ahead and make this look like f of x, f of 5 is 23, so we have the point 5, 23 at the top, and the point 0.03 at the base. What is the height of this triangle? So we have the triangle 5, 20, that has an area, well, it's 1/2 base times height, so 1/2 5 times 20, and that's 100 divided by 2 is 50. Oh, yeah. You're welcome. And then for the rectangle, I guess I've got my colors messed up. For the rectangle, we have a base of 5, a height of 3. We know that the area of a rectangle is base times height. So 5 times 3, which is 15. So that the area, definitely we know the area of the region between x equals 0 and x equals 5, and between the x-axis and the function f of x equals 4x plus 3, it's exactly 65 square units. So we can compare some of the techniques that we're using to approximate, that we'll use to approximate areas like this one. We can see what's going on more easily because we have an exact value that we can compare with. So, what happens when we find the first approximation for n equals 25? We are breaking the interval between 0 and 5 into 25 little rectangles. But each rectangle, it's measured from the right. So if you look at some of the videos, you'll see this is a right Riemann sum. Each rectangle has a little bit extra on top or above the function. And that's why we get 67. And let's go through one of the other If my head is ever wandering around, just put it in a bag and toss it somewhere. It's scary, I didn't laugh. Okay, so we've got the approximate sum, or approximate area, is found by applying some x sub I notation to the function and multiplying by the width of each interval. So let's see what that could be. To find delta x, we are always going to do b minus a over n. So here b is 5, a is 0, n is 25. 5 over 25 is 1/5. And I'm going to let x sub I be 1/5 times I. And that means f of x sub I is f of 1/5 I. Well, that's what is it? 4 is supposed to, okay. So 4 times 1/5 I plus 3. Is this right so far? Please yell if I'm making mistakes, because that'll happen. And here we get 4I over 5 plus, can I write 3 so that it has a denominator of 5?
Multiply by 5.
Say it again?
Multiply by 5.
Yes, good. So 3 is equivalent to 15 over 5. And that helps us out, and we'll see in a minute why. But here's the value of the function for each I. So let's come here. We have the sum, I equals 0 to 25. F of x sub I is 4I plus 15 all over 5. And delta x, what was delta x?
1/5.
1/5. So, let's see, I equals 0 to 25. Can I do something with this? Can I multiply those two fractions? Yeah, sure. So multiplying fractions is across. What is the numerator?
4 plus 15.
Groovy, and the denominator?
25.
Awesome. This 25 in the denominator, I can pull out. So I've got 1 over 25. Sum is I goes from 0 to 25 of 4I plus sum I equals 0 to 25, 15. Is that right? Oh, I wasn't gonna do this one. Oh, well, it doesn't matter. So we have 1 over 25. What about this sum? Can I evaluate this sum? As I runs from 0 to 25, 4I. Somebody help me out.
4 times
26 over 2.
Beautiful. And the sum of the second?
25 times 15.
Alrighty. Groovy Keen? And by having this factor of 1 over 25, do you see that now we can bring it through and just strike out common factors? And let's go ahead and do it this way. So I've got I'm gonna cheat. So I've got 2 times 25 times 26 all over 25 plus 25 times times 15 over 25. So we get 52 plus 15, which is 67. The whole point of what we did last time, and this is sort of a synopsis of what we did last time, is we're playing with the properties of sigma, and we're getting used to this Riemann sum that we're gonna add up and approximate or get the exact area. Any questions about this? So, let's look at the same function. Okay. Here's the definition. Of the definite integral and it's defined using Riemann sums. So this symbol, an elongated S from A to B of f of x dx, where the dx and the elongated S together mean integration, is equal to, so this is the exact area, the limit as n goes to infinity of, we're gonna do something very similar to what we were just doing here. But we're gonna let I run from 0 to n. So we have f of x sub I delta x. So that is our exact value. We already know what the exact value is of the area for the function f of x equals 4x plus 3. Where A is 0 and B is 5. So let's see if we can build this. Again, I want to find delta x, b minus a over n. But this time, what value am I not changing? N, exactly. So I've got 5 minus 0 over n, or 5 over n. And I want to let x sub I be 5 over n times I. Let's figure out our function. So f of x sub I is 4x sub I plus 3, well that's 4 times 5 over n I plus 3. And let's multiply through. In the first term, what do we have? If we multiply 4 times 5 over n I,
5 over n times
good. Here's my f of I. F of x of I. So let's substitute in, let's find f of x sub I times delta x. So we said that f of x sub I was 20 over n I plus 3. And what did we say delta x was?
5 over n.
Good. Just like before, when we were playing with approximated values, we want to multiply through. This time it really doesn't help us to write this as one fraction. So we're going to distribute 5 over n times 20 over n I and times 3. And let's see, 20 times 5.
100
N times n,
n squared n squared.
and then I. Is that right? And then plus 3 times 5 over n.
15.
All right. Now it's a whole lot easier for us to put, and actually, let's do this inside part. Let's find the sum as I runs from 0 to n of 100 over n squared I plus 15 over n. Can we break this sum into two parts? Into two summations?
Yes.
Yeah, sure. So we have the sum as I runs from 0 to n of 100 over n squared times I plus the sum as I runs from 0 to n of 15 over n and at this step, the most common technique is to pull everything to the left side of the summation that doesn't have an I, because only I's are being summed. So we've got (100 over n squared) summation I runs from 0 to n of I. Why is this nice? Why is this sum nice? Do we know what this sum is?
Yes.
Yeah, Groovy King. And 15 over n sum I runs from 0 to n of 1. So here we've got 100 over n squared. What is the sum of the first n integers?
It's n times n plus 1 over 2.
Groovy. And what is the sum of the first n ones?
times 1.
Good. So far, make sure that you're, this is making sense. So I'm gonna pause, so y'all can take it in. Because the next step is algebraic. Well, first of all, what can we do with this second term?
It's just 15.
Yes, it's just 15. Great. And that makes sense. That's the part of this function that was the constant. Constant times the base. Okay. What we're gonna do with this first term, I'm gonna write 1 over n squared as 1 over n times 1 over n. And let's pull out this 2 so that we just have n plus 1, and then we have plus 15. Where did the 1 over n's come from?
The denominator of 100 over n squared.
Yeah, we have 1 over n squared. Do we still have 1 over n squared?
Yes.
Okay, and what we're gonna do is a sort of distribute thing. I wanna write, do y'all mind if I write this as 50, 100 over 2? I'm gonna write n times 1 over n. So this 1 over n is going into the n term, and then 1 over n times n plus 1 plus 50. Because I'm keeping in the back of my mind the fact that I need to let n go to infinity. So, let's see, the first term, the first parenthetical term, what do we get?
1.
Groovy. And here, can I write n plus 1 over n? Is this n over n plus 1 over n the same as what we had?
Yes.
Okay, good. So we've got 50 times, that 1 is gone, n over n. N over n?
1.
And 1 over n. Why is this a nice setup so far? Thinking about n going to infinity. Why is this helpful? The only n we have is where? In a denominator. And if we let a number in the denominator go to infinity, what does that fraction go to?
Just getting smaller and smaller.
Yeah, it goes to 0. So that's really good. I'm gonna distribute the 50. So that I can add the numbers. It really, I believe, is helpful to do as much work as you can outside of the limit, as opposed to doing all of this work with the limit. Because if you don't write the limit every time, once you write it, you have to write it every step, and that can become maddening. So we've got the limit as n goes to infinity of 65 plus 50 times 1 over n. Groovy? What happens as n goes to infinity of the number 65? What happens to the number 65? Does it have an n?
No.
Right, exactly right. It just stays 65. And what happens to 1 over n as n goes to infinity? We already said it, let's say it again.
It becomes smaller.
Well, in the limit, it becomes
Yeah,
Zero.
it's closer to-
and we get 65. So we got this exact answer when we did it geometrically as we got here. Any questions before I put y'all to doing this same stuff with your function? So the try this one is to find the exact area between A equals 0, B equals 4. Is that right? And f of x, 2x plus 1. And I'm gonna call on one of the tables to do this on the board.